I'm at the Chilbolton Observatory in Hampshire, which is part of the UK's space infrastructure. One of this year's new ventures is a small microsatellite called UCube-1. The UK's first national cube satellite has several experiments on board which will explore exciting new technologies. One of these experiments is a small, very light camera which we've designed at the Open University with UK industry, which will take photographs from space. And now our challenge is to prove it can withstand radiation. Satellite images have changed whole industries: agriculture, weather, geomapping, and our understanding of the universe. And current debates occur around the choice between a few big, expensive cameras on large spacecraft developed by governments, or many, many cheaper cameras on nanosatellites, perhaps developed by small to medium enterprises, providing real-time global monitoring. Our work with UCube-1 is looking at the second route. Here in the control room of the Chilbolton ground station, the data will be received from UCube-1 and later redistributed to all the collaborators on the project. And it's universities like the Open University that are key partners in UK's space programme. And this is a life-size model of the UCube spacecraft, and inside it is a small experimental camera which will demonstrate new UK technology. Here's our camera experiment on a small printed circuit board. Called C3D, it actually contains 3 separate imaging sensors. But one of the key things will be to demonstrate that this new technology works without glitches, surviving the space radiation damage. The Earth is surrounded by radiation belts, formed from highly energetic particles. When eruptions occur on the Sun's surface, more radiation particles are released towards Earth. This combined radiation can have a severe effect on satellite electronics. So our challenge is to create imaging cameras that can survive the radiation for longer. So we're hoping our little camera on UCube-1 will withstand the bombardment of the energetic space particles. Then we hope it will be incorporated into larger science instruments. And who knows, one day it may save lives, for example, in disaster monitoring.
NASA's 3-year SMAP mission to measure global soil moisture launches in November 2014. After the protective nose cone, called the fairing, separates, the rocket deploys the SMAP spacecraft. Solar panels, which will generate 14,000 watts of power, unfold and the spacecraft turns the panels toward the sun. Tiny thrusters stabilize the spacecraft. The antenna arm extends from the SMAP spacecraft and the antenna opens. The 6-meter antenna, also called the reflector, is made of strong, thin, gold-plated mesh. The antenna spins so it can measure a wide swath. Employing a combination of active radar and passive radiometer measurements, SMAP covers a swath 1,000 kilometers wide. That's 621 miles. SMAP's radar actively bounces a microwave signal off the Earth's surface to detect physical properties in the return signal. Radar can sense soil moisture through dark, storms, and clouds. And it has a high level of detail, apparent in this 1996 radar imagery of Amazon river flooding, part of a NASA Measures Wetlands project hosted on the Alaska Satellite Facility website. SMAP's radiometer passively senses microwaves naturally emitted by soil moisture, such as in this 2011 radiometer imagery. Together, SMAP's instruments track soil moisture levels over time in any particular location. For example, SMAP tracks changing conditions, such as in this imagery showing that soil can only absorb so much moisture before a river floods. Researchers can use SMAP data to create time series graphs of their study areas, developing different ways to visualize and detect trends in soil moisture levels. In another kind of visualization, this model shows how SMAP data will reveal the planet essentially breathing, taking up and releasing carbon. SMAP data will be freely available to the public starting in spring 2015 from the Alaska Satellite Facility SAR DAC and from the National Snow and Ice Data Center DAC.